In 2015, a cybersecurity researcher named Chris Roberts was removed from a United Airlines flight by FBI agents waiting for him at the gate. He had been tweeting mid-flight about the aircraft's avionics systems. The FBI's subsequent investigation produced a search warrant affidavit that alleged, and Roberts later acknowledged, that he had connected a laptop to the in-flight entertainment system under his seat, accessed a portion of the aircraft's internal network, and issued a command that he claimed caused one of the aircraft's engines to briefly change its thrust output. He was never charged. The airline denied the incident ever occurred as described. The FBI affidavit used the language, "he stated that he had," rather than, "it is confirmed that." The truth of exactly what happened on that flight remains disputed. But here is what is not disputed. The FAA subsequently issued a special Airworthiness Information Bulletin, a formal regulatory communication, acknowledging that the potential for unauthorized access to aircraft systems through passenger-accessible networks was a documented concern requiring active mitigation. Not a theoretical concern, a documented concern. The regulator responsible for the safety of every flight you have ever taken has formally acknowledged in writing that the network architecture of modern commercial aircraft creates cybersecurity vulnerabilities that require active management. What those vulnerabilities are, specifically, is not fully public. What has been demonstrated by researchers in controlled settings is more than enough to understand why it matters.
To understand the vulnerability, you need to understand how modern commercial aircraft connect their systems internally. Older aircraft had completely isolated systems. The avionics, the flight management, navigation, and control systems operated on dedicated wiring with no connection to passenger systems. The in-flight entertainment system was a separate, standalone network with no pathway to anything operationally significant. Modern aircraft, specifically those designed in the 2000s and later, were built with a different architecture. The Boeing 787 and Airbus A350, the most technologically advanced commercial aircraft in service, use a common network architecture based on ARINC 664, an aviation-adapted version of standard Ethernet networking. This architecture was designed to reduce weight, reduce wiring complexity, and allow more flexible data sharing between systems. It achieves all three goals. It also creates something that older aircraft never had, a networked environment in which different aircraft systems share common infrastructure. The Boeing 787's network architecture, as documented in FAA Special Conditions filings, divides systems into three domains: the aircraft control domain, containing flight-critical systems including avionics, navigation, and flight management; the airline information services domain, containing operational and maintenance systems; the passenger information and entertainment domain, containing in-flight entertainment, passenger Wi-Fi, and connectivity systems. The FAA's Special Conditions document, publicly filed in 2008, stated directly, the Boeing 787 airplane may be connected to the Internet or other network/services via its passenger entertainment domain. This connection could expose the aircraft systems to unauthorized access. That sentence was written in a public regulatory filing 16 years ago. The question is not whether the risk exists. The question is what has been done about it since.
The cybersecurity research community has been probing aviation network architecture with increasing technical depth since approximately 2010. In 2013, researcher Hugo Tesso presented at the Hack in the Box security conference in Amsterdam a demonstration of attacks on aviation navigation systems using a software-defined radio and a commercial Android application. His demonstration targeted the ACARS data link system, the automated aircraft communication system described in a previous video, and the ADS-B position reporting system discussed in the GPS spoofing episode. Both systems, he demonstrated, accept data inputs that are unauthenticated, meaning there is no cryptographic verification that a received message actually comes from a legitimate source. The FAA's response to Tesso's presentation was careful and precise. They stated that his demonstration had been performed on PC-based aviation simulation software, not on actual certified avionics hardware, and that certified avionics systems contain additional layers of protection not present in simulation environments. This response is technically accurate. It is also incomplete. Because the question Tesso's demonstration raises is not whether his specific tool would work exactly as demonstrated against certified hardware. The question is whether the fundamental communication vulnerabilities, the lack of authentication in ACARS and ADS-B, that his demonstration exploited in simulation, exist in the same form in certified hardware? The answer, documented by multiple independent researchers, is that they do. The systems transmit unauthenticated data. Certified avionics hardware receives it. The additional layers of protection the FAA referenced are architectural controls, firewalls, domain separation, monitoring systems, that reduce the risk but do not eliminate the vulnerability at the protocol level.
The aviation industry's response to cybersecurity vulnerabilities is both more sophisticated and more opaque than the response to any other category of aviation risk. Physical safety risks, structural failures, propulsion anomalies, weather hazards are managed through a regulatory process that is largely public. Accident reports are published. Airworthiness directives are published. Research findings are published. Cybersecurity vulnerabilities in aviation systems are managed through a process that is deliberately partially classified. The FAA's Aviation Cyber Initiative, a coordinated effort between the FAA, the Department of Defense, and the intelligence community, operates with a public-facing component and a classified component. The public component issues guidance documents, safety communications, and regulatory requirements for cybersecurity practices in aviation systems design. The classified component, which receives threat intelligence from U.S. Cyber Command, the NSA, and allied intelligence agencies, assesses specific current threats to aviation systems that cannot be publicly disclosed, because doing so would provide operational detail to the adversaries generating those threats. What can be said from publicly available sources? The Government Accountability Office issued reports in 2015 and 2020, specifically addressing aviation cybersecurity vulnerabilities, finding in the 2020 report that the FAA had made progress in developing cybersecurity oversight, but had not yet implemented a comprehensive strategy for addressing cyber threats to aircraft avionics systems. A comprehensive strategy for the systems that control every aircraft you fly on was not yet implemented as of 2020. The 2024 status of that strategy is partially classified.
Here is what can be said with certainty, based on public documents, regulatory filings, and researcher demonstrations that are verifiable. The network architecture of modern commercial aircraft connects systems that were previously isolated. The communication protocols used by aircraft systems, ACARS, ADS-B, and others, transmit data without cryptographic authentication. These vulnerabilities have been demonstrated in controlled research settings by multiple independent researchers at multiple security conferences. The FAA has formally acknowledged that these vulnerabilities are a documented concern requiring active mitigation. The mitigation measures currently in place, domain separation, network monitoring, physical access controls, reduce the attack surface but do not eliminate the fundamental protocol vulnerabilities. The cryptographic authentication of ACARS and ADS-B, the fix that would address the root vulnerability, has been in development since the early 2010s. ADS-B authentication mechanisms have been under research and standardization development for over a decade. Full deployment of authenticated ADS-B across the global commercial fleet is not currently scheduled before 2030 at the earliest. The gap between vulnerability acknowledged and vulnerability fixed in aviation cybersecurity is not measured in months, it is measured in decades. During those decades, the aircraft are flying, the systems are connected, the protocols are unauthenticated, the researchers keep finding things, the regulators keep writing guidance, and the passengers keep connecting to the in-flight Wi-Fi on a network that shares infrastructure with systems whose cybersecurity posture is managed by people who cannot tell you everything they know. Follow for more about the invisible threats operating alongside every piece of aviation technology you encounter, the documented risks, the classified responses, and the gap between them that everyone in aviation security is working to close.